All right, so I posted this video earlier today and I was told that there was no video. So let's hope this time the video works. So this is a difference quotient. And again, the goal here is that we're going to use this formula as it applies to a function. And then in the end, we're going to set h equal to 0. Let's see if we can get started here. So let's look at a function. So we have f of x equaling 3x minus 4. We are going to go through step 1, which is the identification that we need f of x. We're always given f of x, so we're going to throw that over here. Step 2 is to find f of x plus h. And we want to make sure that we're just grabbing this information and we're throwing it everywhere we see an x. Now, in case here, there's only one place to throw the x. So let's toss it in and we should get it over here. And you can see that now f of x plus h is 3 times the quantity of x plus h minus 4. And step 3 is to use the difference quotient. And in the end, we want to set h equal to 0. And I want to point out that right now you have an h down here, and you cannot make a denominator 0. So one of our goals is to get rid of this. And I'll kind of explain that through the different examples I've got going on. So let's go and see what we can do. So what we're going to do is we're going to ultimately take our f of x plus h, which is all of this information, and we're going to throw it here. And then we're going to take all of our f of x and we're going to throw it here. The next slide will show all of that inserted. So there it is. Okay. So here is our f of x plus h. I put it in brackets minus our f of x. I put that in brackets because we want to make sure that we are in fact distributing this negative. And if you forget brackets, oftentimes it's easy to forget that. So let's do that. Let's distribute this negative and then erase our parentheses, and I'll distribute this 3 at the same time. Okay? I'm going to call this the moment of truth. Our goal at this point is to cancel everything that does not have an h. So I start on the right-hand side and I say, well, I have a positive 4. I'm going to cancel a negative 4. I have a negative 3x. I'm going to cancel a positive 3x. So let's cancel those out. And we can see and look and go, all right, the only thing left has an h. That's good. If we had anything left here that was not associated with an h, we would have done something wrong. And that's kind of an indication. So that would have been a place I would have kind of looked back up here to make sure I did everything right. But we're good. So let's rewrite this right here. And now we can say, hey, these h's will cancel. And I want to point out that we do want to make h equal to 0, but in this particular example, we're not going to be able to, because the h's are just going to go away. So the answer to this is 3. Now let's look to see why the answer is 3. So we have an understanding of at least why we do the problem. So let's look at the original graph. F of x was equal to 3x minus 4, and there's kind of a rough graph of that, crossing the y-axis at negative 4 at a slope of 3. And if you look here, this is a straight line. What the definition of a derivative is that's a calculus term. What the difference quotient, what the difference quotient is really doing for us is it's giving us the slope of a tangent line. A tangent line is a straight line that only touches the curve in one spot. But if we have a linear equation, the tangent line is the equation. So notice that the slope of this line was 3. And that's why the answer was 3, because we're really after the slope of that straight line. And because this started off as straight line, it should match the slope of the line. Okay? So let's go to a different example and see what we can do with the next one. So here's the difference quotient. We're going to use it to evaluate f of x equaling 6 minus 7x. I kind of slid in here the difference quotient so we can kind of see that. Let's go to step 1 by identifying our f of x. Again, we always have that, so let's toss that in. Step 2 is to find f of x plus h. Again, we just want to take this information and throw it everywhere we see an x, which is going to give us f of x plus h. So here it is. Okay? So now what we can see is we needed this, right? It's right here. Well, that is now going to be all of this. I'm going to take all this information and put it right here. I'm going to take all of this information. I'm going to put it right here. So let's do that next. Again, I use brackets on my f of x plus h. I use brackets on my f of x. So the only thing I've got left to do here is I want to distribute this negative 7, and I want to distribute this negative 1. So let's do that. Again, I'm going to keep calling this the moment of truth. Everything that doesn't have an h should cancel. Always starting on the right-hand side, because notice none of these had h's, so it would be easier to start over here to cancel things out. I have a 7x that should cancel with a negative 7x. I have a negative 6 that should cancel with a positive 6. Let's do that. And then I just looked. Now that's the only thing left. It has an h, because remember, our goal is to get rid of this. So let's write that. These will cancel. And I'm back in the situation where I can't make h equal to 0 because there aren't any h's left. But notice what happened. I'm going to get an answer of negative 7, which matched the slope of this linear line. So if you have a linear equation, the definition of a derivative should give you the slope of that line. Okay? But what happens when it's not linear? So let's look at an example where it's now quadratic. So this is not a linear equation. This definition of a derivative is not going to give us a number. It's going to give us a formula in this particular instance. For all non-linear equations, the definition of a derivative will simply give me the formula for the slope of those lines. And I'll show you that in the end of this problem. So here's step 1. Let's find our f of x. Well, we have it, so let's throw it in. Step 2, let's get our f of x plus h. Again, I just want to take this information here and throw it everywhere I see an x. So there's only one place, but if there was an x here, I'd throw it there as well. So let's throw that in. Now here's a major mistake I see oftentimes. Somebody's going to take this problem right here and simply square the x and square the h, and that's wrong. What this represents is the quantity of x plus h times the quantity of x plus h. There's 2 of those. So you ultimately have to FOIL this. So let's do that underneath. So if I FOILed this, I get x squared plus 2xh plus h squared, and still that minus 4 comes for the ride. And since these parentheses are not necessary, we'll end up getting rid of them. But this right here is now our f of x plus h. This whole thing is going to replace that. And there's my f of x. It's going to replace that. So let's do that. It's right there. Okay, again, I want to remove these parentheses. So I'm looking for anything I need to distribute. Only thing I've got to distribute here is this negative. Once I distribute this negative, I can get rid of all these parentheses. So let's do that. Again, once the parentheses are gone, we're now situating ourselves with that moment of truth of saying I need to cancel everything that does not have an h. So I have a positive 4. Well, it's going to cancel with a negative 4. I have a negative x squared. Well, it's going to cancel with a positive x squared. So let's cancel those out. And then just look. Hey, that has an h, and that has an h. And that's what we want. The only things that did not have an h are now canceled. So let's rewrite this. And let's not forget our goal. We want to remove this issue because in the end, we want to be able to set h equal to 0. So the only way we can do that is if we can take an h out of the top. So let's factor out an h. And now these will cancel. Now what does that leave me with? It leaves me with 2x plus h. And at this moment, we can now set h equal to 0. So we can make this a 0. And what is that going to give me? It gives me a formula. So notice the first 2 examples gave me a slope. Well, that was because the first 2 examples were linear. This does not give me the slope. it gives me the formula that will give me this slope. So let's look at what this thing would look graphed. Here is the original function. Definition of a quotient was 2x. And let's look at its graph. And I don't know why I said definition. This is the difference quotient. So the difference quotient was 2x. But this was x squared minus 4 roughly graphed. So remember, let's see what this is going to do for us. Let's just take a value, say x equals 3. And that would give us a point on this graph somewhere up here. And what I was saying before was all this is really going to do for us is it's going to give us the slope of the tangent line at this point. So let's draw a tangent line. And if you remember from geometry, tangent line is just a line that touches the function or the curve in one spot. So there it is. It is linear. We have a formula for the slope of that line. So let's take this 3 and throw it into 2x. So again, I'm just using this, and I'm throwing a 3 in, and it gives me a slope of 6. So the slope of this line is 6. Now the difference quotient answer is just 2x. This is more of getting closer and closer to a calculus. So this is where we're going to extend into more of an extra credit concept. So let's write that here. Extra credit concept. The difference quotient identifies the equation for the slope of the tangent line along a curve. If the function is linear but not vertical, the difference quotient will give us the slope directly. Notice this was not a linear equation, therefore the difference quotient just simply gave us the equation for that slope. Okay? All right, let's look at another one. Again, another non-linear equation. Here's a quadratic. We're going to evaluate this by using the difference quotient. Here it is. And in the end, we want to set h equal to 0. So here's step 1. Let's throw in our function. Let's find our f of x plus h. I'm going to take this and throw it everywhere I see an x. Again, I want to make a point that if there was an x here and an x here and an x here, we'd throw it in all 3 places. But in this problem, there's only an x in one spot. So let's toss that in. There is my f of x plus h. Now, it's okay to grab this thing right here and just replace it. But notice we would ultimately have to expand it anyway. So we might as well just do that now. So x plus h squared is your x squared plus 2xh plus h squared. Now I can distribute this 2. And there is my expanded x plus h right there. So all of this information will go here. All of this information will go here. And I'll use brackets. So let's do that. And again, I just want to make sure that I can remove these parentheses. So the only thing to do now is to distribute this negative. So let's do that. And once the parentheses are gone, we're thinking, all right, I want to remove everything that does not have an h. So I start on the right-hand side and say, well, I have a negative 1. It's going to cancel with a positive 1. The negative 2x squared, it's going to cancel with a positive 2x squared. So let's cancel those out. And then we just look, hey, that has an h and that has an h. So we should feel fairly comfortable we're doing this right. So let's write that down here. And we want to remove this h because we want this to be 0. But it can't be 0 down here, but it certainly could be 0 up here. So let's take out an h. And now we can cancel out our problem. So this is what's left, 4x plus 2h. And now that can equal 0. So let's take our h and set it equal to 0. And we get 4x. Now again, what this is this is the equation that is going to give us the slope of the tangent lines along this curve. So let's go look at what that would be like. So here's the original function. The difference quotient was 4x. And that's a rough estimate. And, I'm only going to put a tangent line in one spot. But, I mean, there could be a tangent line here. There could be a tangent line here. There could be a tangent line here, here, here. I'm just going to pick x equaling 1, saying, well, that point should be somewhere up here. Oop, wrong spot. At 3. And if I drew a tangent line right through this point, this equation will give me the slope of this line when x is 1. So let's throw in a 1 into that. So again, I'm just using that here, and I'm throwing the 1 where the x goes. And it's telling me that, all right, at this particular moment in time, when x was 1, the slope of the tangent line is 4. So the slope of this line is 4. And if you're still thinking like, well, what's the point of that? The point really kind of comes into the calculus realm, where in calculus, this would be called a derivative, and this would actually be the velocity of this position function. So when you get into physics or calculus, it'll become a little bit more, it will make a little bit more sense. But the first derivative in calculus is called velocity, where the second derivative is called acceleration. So this actually will start to be applicable. But here's the extra credit for pre-cal. The slope of the tangent line along the curve of f of x when x equaled 1 is 4. All right? All right, nice work.